Okay, so in this video, I'm going to perform a convolution example between two functions. Just a word of warning: this is difficult to explain. I found this the hardest concept to really convey. So please don't worry if this doesn't make too much sense, because I've done another MATLAB video afterwards with these two functions, which in my opinion is much better than this for actually explaining it, because I created a function that could actually swipe across and explain the limits of integration, which is really, really important here. In fact, it's really the most important part of convolution, which is understanding the different phases of how one signal moves across another signal, and integrating at different limits with each phase. So I'm going to go straight into this question and then have a look at the MATLAB video afterwards, which comes on automatically, and then maybe come back to this at the end. Let's have a go. So we've got a function here, which is f of t is 1 between 0 and 1 and 0 otherwise. So that's what we have over here, between -1 and 1. That's wrong, sorry. It should be -1 and 1. It's going to take the value of 1. And g of t is e to the power of t between 0 and 1 and 0 otherwise. Okay, and what we're going to do, we're going to convolve the two signals so that we're going to basically pass g of t across f of t for all values of t, and we would like to get a description, a function that describes what the magnitude of the area of overlap of both those functions are for all values of t. So let's go straight in. Now, do you remember one way that well, a good approach to try and figuring this out, this problem, was to invert g of t in the y-axis, or reflect it in the y-axis rather. So we end up with something looking like that. And then what we're going to do, we're going to add, so that's to say g of minus t. And then what we're going to do is that, do you remember we said before, if we have or a normal function and we add a positive shift, we just do, say, sine t plus a, and the plus a is going to shift it to the left. If we do sine t minus a, it's going to shift it to the right. But if we reflect a function in the y-axis and then we do a plus a, so sine of minus t plus a, it's actually going to have an effect of shifting the function to the right, and just like a sine of minus t minus a is going to shift the function to the left. Well, since we have a function here being being reflected in the y-axis, g of minus t, if we add a value to the argument, so say g of minus t plus 1, it's going to shift that function to the right. If we add g of minus t minus 1, it's going to shift that function to the left. And that's going to be really useful, because what we're going to do is create a dummy variable, call it x or tau, whatever you want, make things looking exactly the same. But then the shift that we're going to add is going to be plus t, which is very clever, because that allows us to derive a function where, as we increase the value of t, we're effectively swiping the red function across the t-axis, which is quite clever. It's quite a neat trick. So, so let's go ahead and rewrite f of t and g of t in terms of tau, and try and add a plus t shift so we can see what's going on. Okay, so what we have over here is, I've just changed the axis to tau. I've kept f of tau the same as f of t. Okay, it's just changed the t variable. It's exactly the same function. Now, don't panic when you see this, because there's a little bit of things going on here, a few things going on here. First of all, just it's hard to say pretend, but pretend all I've done is shifted g of t in the y-axis to g of minus t, and then just replace t with tau. What I would end up with is exactly that thing over here. Yeah, I'll draw it in pencil, and then hopefully I won't get too confused. That would be what g of minus tau looks like, that pencil line there. Yeah. Now, all I've done is that if you do g of minus tau plus t, or plus a, plus anything you want, it's going to shift it in the right direction, in the right-hand side, isn't it? So if we do that and say g of minus tau plus t, when t is negative, it's going to shift it to the left. And that's exactly what we have over here. We have g of minus tau, which is this pencil line over here. It's just g of tau reflected in the y-axis. And then plus t. And t here is going to be negative, yeah, because we've been shifting it to the left, and we want to shift it a little bit to the left so that we can start shifting it to the right, i.e. incrementing t. And then as we increment t, we'll be able to integrate and find the product of those two functions. What I'd like to say over here, that we can call t over here, let's say minus 2. It would be, say, roughly minus 2 over here. When t gets to minus 1, the leading edge, this is the leading edge, because it's leading the function, will overlap directly with the back edge, or the trailing edge, of f of tau over here. Yeah? And as we start to swipe through, t is going to get larger and larger. So let's think about what the convolution is actually going to look like. Now, we said before that the definition of a convolution function is going to be... actually, no, I don't want to do the definition. Let's try and work things out logically. So it's going to be something between infinity and minus infinity for tau, because this is a tau scale now, for all the values of that. And it's going to be the product of this function and this function, isn't it? Which is f of tau dot product with g of minus tau. Agreed? D tau. But we've got a plus t over here that will allow us to, once we've integrated the function, to have a function in terms of t that will give us the integration product of the overlap of both functions for all values of t. It sounds really, really complicated, but it isn't. You'll see the MATLAB file later on, which will hopefully clear things up. So what we're going to do g of minus tau plus t, and that will give us a product in terms of t that will describe the integration product for all values of t. Now, we can't just do this in one go. And the reason we can't do this in one go is because of something that I'm going to explain now. And this is where it gets, this is the most tricky part. On paper it's harder because I can't physically shift the function. On MATLAB I can. So if you have a look on the MATLAB file later on, it's a lot easier. It's explained, I think, a lot better. But you can see here, as t is, say, minus 2, put minus 2 over here, we can easily see that the product of the area of overlap is 0. When t is minus 1.5 over here, it's also going to be 0. When it's minus 1, it's also going to be 0, but it's now going to be increasing. So something is happening at t is minus 1 to a certain value. Now, when this function is at minus 1, it's going to look something like this, yeah? As this function starts to move across, we're going to have an area of overlap of those two functions, yeah? It's going to look something like that. And what we're going to do is that if you can visualize this function here, g of minus tau plus t, moving to the right-hand side, that area of overlap is going to get bigger and bigger and bigger. And the integration product is going to be between whatever value of tau is, which is going to be t, yeah, as t gets larger and larger, and minus 1. That is really important that we understand why that's true, that the limits are going to be between tau and minus 1. Not t and t minus 1. Remember, if this is the leading edge over here, this red line, yeah, and we'll call that t, then the trailing edge is always going to be minus 1 units behind. So we can call that t minus 1. We're not going to be taking the limit between t and t minus 1. Why not? Because, and this is explained a lot better on the MATLAB video, the function of f of tau, the product of those two functions, f of tau and g of t minus tau, is going to be changing, is going to be different, is only going to be consistent between t and minus 1. Because beyond minus 1, the function f of tau is not going to be 1 anymore, it's going to be 0. Don't worry if you didn't understand that. Please wait for the MATLAB video. It explains it so much better. But let's do the integration and then maybe come back to this afterwards. It really is the most tricky part to understand. Now, f of tau, we know that's going to be 1, and that's dotted with g of t minus tau, which is going to be e to the minus tau plus t d tau. And that's going to be the integration product is going to be e to the t dot e to the minus tau d tau between t and minus 1, and that's tau equals minus 1 and t. Yeah? So let's carry on with this. Now e to the t is a constant, so we can take that out. So we can say e to the t between t and tau equals minus 1 of e to the minus tau d tau, which is going to be e to the t times minus e to the minus tau evaluated between t and minus 1, which is going to be equal to e to the t, take the minus out, e to the minus t minus e to the minus minus 1. That's going to be minus e to the t times e to the minus t minus e equals e to the t, that's going to be e to the naught, it's going to be 1 minus e to the t plus 1. So that's going to be the convolution function between, do you remember that we said that this has to start at minus 1? Because when t is minus 1, remember g of minus tau plus t, when t is minus 1, that's when it begins. And that's going to continue until t equals 0. Why 0? Because at 0, what's going to happen is that the this is going to start to look like this over here, like that. And then as we swipe the function across, it's going to maintain its value. If we continued with the limits between t and minus 1, we're going to be evaluating a function that is larger, i.e. that's e to the t minus tau between t and minus 1, and that's not true, because e to the t minus tau is only valid between 1 unit across, between t and 1 unit behind t. So as we move that across, while it's constant, the limits are going to be between t and t minus 1. Please don't worry if you didn't understand that. I wouldn't have understood that if I just explained it that way. Wait for the MATLAB video, it's much, much clearer, and then maybe come back to this. So we now know that between minus 1 and 0, the convolution function is going to be 1 minus e to the t plus 1. Sorry, that should be a minus. So it's actually going to be e to the t plus 1 because I left out a minus over here. So it's going to be c of t equals e to the t plus 1 minus 1. Not that one, sorry. Okay, now for the next stage. Now I know that this is a bit of a wonky drawing, but it should be okay. G of minus tau plus t again, yeah? And now t is beginning, t actually at this point is 0, yeah? Which kind of makes sense because now it's g of minus tau. It's just g of tau reflected in the y-axis. And as we sweep across, the integration product is going to be f of tau, because remember it's going to be, we're looking at the product of f of tau dot g of minus tau plus t, yeah, d tau. And f of tau is going to remain at 1 between t is 0 and 1, and g of minus tau plus t is going to remain at e to the minus tau plus t between values of t equals 0 and 1. So we'll say 0 and 1. This is where this is the very tricky bit, really. Just thinking about evaluating what the functions are going to be at the different limits and then setting the limits correctly. So between 0 and 1, the limits are going to be t and t minus 1, because remember these are dynamic limits that are going to be applicable when those functions remain at those values, meaning that between here and here, as the red function moves across, between t equals 0 and t equals 1, between g of minus tau plus 0 to g of minus tau plus 1, it's always going to maintain the value of e to the minus tau plus t, and f of t will always be 1. That's why we can say that this integration is going to be between t and t minus 1 of 1 dot e to the minus tau plus t in that range between 0 and 1. d tau. So if we integrate that, we're going to get the result of, let's just do that integration here. So it's exactly the same as before. We can take e to the t out. It's going to be e to the minus tau d tau between t and t minus 1, which equals minus e to the t, e to the minus tau evaluated between t and t minus 1. And that's going to be minus e to the t, e to the minus t minus e to the minus t plus 1, I believe. And that's going to be equal to minus e to the t. Oh, sorry, I can just do that directly. It's going to be minus 1 plus e to the 1. So we can say that the convolution function is going to be e to the 1 minus 1. So we can go back up here and say c of t equals e minus 1 between 0 and 1. And at that point, the function would have shifted over here when t equals 1. Yeah? Okay, so now let's think about what happens when t goes beyond 1. So remember, this is the value of t, whatever it is. Now, as t increases beyond 1, we can see that the area of overlap, the magnitude, is going to be it's going to be over here. Yeah. Up to that point there. Yeah. Now, we can see that as g of minus tau plus t is increasing and increasing and increasing, what's going to happen is that the magnitude of the area of overlap is going to get thinner and thinner and thinner, meaning that this window over here is going to get more narrow and more narrow and more narrow. And what's going to happen is that the red, if you imagine where my pen is, that's going to be the end of the limit, and where my pencil is going to be the beginning of the limit. And as g of minus tau plus t is shifted more and more to the right, the window of overlap is going to go like this. It's going to get thinner and thinner and thinner and thinner and thinner until it gets to 0 over here. So we can say then that the integration is going to be is going to take the maximum value of 1 and the minimum value over here. And remember, that has to be in terms of t. And since the trailing edge is trailing behind the leading edge by a unit of 1, that value is always going to be whatever t is minus 1, isn't it? Yeah? I hope that makes sense, what I've done there. And the reason why, again, we can't evaluate it from t and t minus 1 is because, can you see the function f of tau over here? It ends over here when tau equals 1. So the upper limit has to be 1. If we were evaluating the function between t and t minus 1, we would be evaluating the wrong functions, because we would be, well, we'd get an overestimate, because we would be saying, well, f of tau is actually 1, and g of minus tau plus t is g of minus tau plus t. Well, g of minus tau plus t is g of minus tau plus t between t and t minus 1. But f of tau is not. F of tau is only 1 between 1 and t minus 1. I hope that was clear. So f of tau is 1 dot e to the minus tau plus t. And that is true as t goes from 1 to... as t goes from, let's think about this, where did we end off? We ended off when t is 1, so it's when t starts at 1, and when it goes to 2, that's when it's going to be valid from, that's when it's going to end. And the integration will only be this window. Remember, as this window is getting closer, as the window is closing in this direction, it's getting thinner and thinner and thinner and thinner and thinner. Okay, so over here, the window is going to be between t and 1, and t over here is 1. Yeah, well, t is always going to be between 1 and this value here. So it's going to be 1 and t minus 1. And as t increases to the value of 2, the pencil limit is going to tend towards 1. So eventually we're going to be tending towards a limit between 1 and 1, i.e. 0, a very, very thin window, and then that's going to be 0. So that's why that part, the third phase of the integration, is going to be this over here. So there we have the convolution function for the final phase. Now let's summarize. This is the summary here of results. Between minus 1 and 0, it's going to be e to the t plus 1 minus 1. Between 0 and 1, e minus 1. And between 1 and 2, e minus e to the t minus 1. So that was quite hard to really describe what was going on. And really don't worry if you didn't understand that, because I'm going to have a look at MATLAB now. And I'm going to explain that using a function slider, and then have a look at what this convolution actually looks like and see if it makes any sense. Okay, so what I'm going to do over here is try to explain graphically the process of the convolution of these two functions that we were looking at. So the blue line shows the input, and we've got maybe a pulse that lasts for 2 seconds, and then the red line is the g of t function, or the signal that we're convoluting. And this should hopefully explain a little bit about the process of the integration of convolution and how it rises to the function that we generated. And I really want to pay very close attention here to the limits, because the limits of the integration are what are really important to understand here. So what I've done is that I've taken the original g of t signal, which was originally between 1 and 2, I believe, or 0 and 1, and it was between 0 and 1. And it kind of looked like this. It was going up all the way here and then coming down. And then what we did is that we flipped that in the y-axis. So we get, instead of e to the t, we've got e to the minus t. So that looks like this. And then what we did is moved it, or we displaced it to the left. And the idea is that we're going to sweep this function across this blue rectangular signal, and we're going to try to figure out the magnitude of the area of overlap of both of these functions as this function is swept across to the right. So I've built in a sweep variable here in MATLAB, and hopefully this is going to work. So as I move it to the right, you should be able to see, there we go, the function is starting to move to the right. This is fixed. So t here, this variable, the sweep variable, represents t. And t represents the leading edge on g of t, which is this function over here, which is minus 2 over here. And that is representative in the integration as well. When we had plus t, do you remember we changed the dummy? We made a dummy variable of tau or x, and then we said that the convolution function would just be g of t. It'd be f of tau, g of minus tau, plus a, or plus a certain variable, which we then substituted for t, because t is going to be the original function which we want the convolution to be representative of. Sorry. So basically what we're going to do is that as we sweep, so at that point, when we have f of tau times g of minus tau, that's just flipping the red function in the y-axis over here. And then when we do plus t, do you remember we said that when we have a function that's been mirrored in the y-axis, and we do a plus, we have a positive shift, that's going to shift the function to the right-hand side. So that's what we're doing here. So as t increases, this is going to move to the right. Normally with a function shift, a positive shift will shift the function to the left. But since this is a reflection of the y-axis, it's going to shift it to the right. So as we move t to the right, at 1.6, this should move to the right. There we go. And the convolution, the area of overlap at this point, just over here, is 0, because there's no overlap yet. So let's keep moving to the right. Minus 1.4, still no overlap. 1.2, minus 1.2, still no overlap. And when we get to minus 1, that's where they begin to overlap. So we can see here that the convolution function at minus 1 is going to be 0. Let's keep going. As the red function is now moving across, you can see we now have a magnitude of overlap. Now this is really important to understand how we get the area under that overlap. What we do is that we're going to integrate where the red line is from the red line to the blue line. As the red line starts to move, as t starts to get larger, we're going to be integrating from t, whatever the value of t is, to minus 1. We are not going to be integrating from t to t minus 1. Why not? Because the function of f of t is 1 only between t and minus 1. If we dot product and take the integration limit from t to t minus 1 over here to this point over here, then we're not going to get the correct valuation, because we would be evaluating an integrand of a function of 1 and e to the minus t for all values between t and t minus 1. And that's not correct, because the function f of t only remains 1 between t and t equals minus 1, not between t and t minus 1. I hope that makes sense. If we keep scrolling to the right, we're shifting to the right, we're still going to be integrating between whatever value of t is and minus 1. That's why the original limit is between t and t equals between tau equals t and tau equals minus 1, as the function is being shifted through this phase of the cross signal. Now let's keep going. So we're still going to be integrating between tau equals t and tau equals minus 1. Remember, because if we integrate between tau equals t and tau equals t minus 1 or t minus 2, whatever the displacement is between this line and this line, we're going to be dot producting the function valuated at 1 here and e to the minus t here. Well, e to the minus t is correct between t and t minus 1, t minus 2. But f of t is only 1 between t and t equals minus 1. Okay? If we were to do an integration between t and t minus 1 or t minus 2, I've forgotten the distance here, it looks like it's 1, then what we're going to get is a product that's going to be too high, because we're going to be evaluating an integrand that is assuming we've got a function that is 1 between here and e to the minus t between here and here. Well, that's not true. We've only got e to the minus t between here and 1 between here and here, not between there and there. I hope that's clear. So let's keep going. Right, now that both functions are overlapping completely, the integration limits are now going to be between t and t minus 1. Why? Because the function e to the minus t is e to the minus t between t and t minus 1, and the function f of t is 1 between t and t minus 1. Therefore, we can take the integration with those limits and those functions, because those functions will have those values between t and t minus 1. So as we move the function across now, we're still going to take the limits between t and t minus 1 for all values of tau between here and between there, and as we shift the function. So let's keep shifting the function further and further. We're still going to be taking the limits between t and t minus 1, again, because the function g of t is e to the minus t between here, and the function f of t is indeed 1 between here and here. Let's keep going. By the way, when I'm saying e to the minus t, I'm obviously including the shift here, because e to the minus t is obviously going to be changing, but here it's not, because we're just mirroring the function and dragging it across. So that's obviously with e to the minus t plus e to the minus tau plus t. Yeah. So we're still taking the limits of integration between t and minus t. But what happens when the overlap starts to exit? Now, when g of t starts to exit the function f of t, if we took the limits of integration between t and minus t again over here, well, that would give us a too high a value, because we've got e to the minus tau plus t over here going on, but we do not have f of t equals 1 between t and t minus 1, only between this value here, tau equals 1, and this line over here. And that line over here, relevant or relative to this red line, is going to be t minus 1. So the limits of integration as the function g of t starts to exit the function f of t is going to be between tau equals 1 and tau equals t, which is this red line, minus 1. And that will give us the reference over here. So again, those limits of integration at this point are going to be tau equals 1 and tau equals t minus 1. Let's keep going. And we can see that we're only going to be dealing with the integration between here, tau equals 1, and tau equals t minus 1, which, by the way, at this point is going to be approaching 1. And then as we go to 1.8, t equals 1.8, we can see that the limits of integration are going to be between tau equals 1 and tau equals t minus 1, which is going to be 1.8 minus 1, which is 0.8. So we can see that the limits now between 1 and 0.8, and the limits here are going to be between 1 and 0.9, because t is now 1.9, 1.9 minus 1, which is the displacement between the two lines here and here of g of t, is going to be 1.9 minus 1, so it's 0.9. So we're going to be taking the limits of integration between tau equals 1 and 0.9. So we can see that that sliver is getting really, really small now. And then, obviously, when it actually gets to 2, there's going to be no overlap, and 2 minus 1 will be 1. So the limits of integration now will be between 1 and 1, which are going to be 0. In other words, an infinitesimally small sliver, no sliver, really. So based on this, we can now see what the magnitude of the, or a function describing how the magnitude of the area of overlap of those two functions changes for all values of t. which is obviously going to be 0 up until -1, and then it's going to be 0 for t is greater than 2. And I'm just going to sweep across again, just so maybe you can get some kind of a guess to see what the that convolution function is going to look like. So maybe draw what you think it's going to look like. Replay that last part, have a draw, see what you think, and then we'll look at the answers in a second. Okay, so now we're ready to have a look at the answer. So the green dotted line is the convolution function, and what you can see is very beautiful. It's really does describe what we should expect to see, which is very satisfying. As the g of t begins to sweep at the value of t equals -1, the convolution function starts to take a positive value. And what you can see is that the rate of change is increasing and increasing and increasing up until the point when t equals 0, and there's no further increase. Now, why that's happening, we can understand why that's happening, is because as with this, we've got a negative exponential decay going on. We can see that as we start to sweep this function further and further right, the rate of change or the rate of increase and overlap is getting greater and greater and greater, because this slope is getting higher and higher, is increasing at higher rates as we sweep this red function across. So that's why we have this green increase, which is kind of like an exponential increase here. And we would expect that when we when g of t enters f of t, we're going to get an exponential increase. And also when g of t exits f of t, there should be an exponential decrease for exactly the same reason. Remember, initially, this part of the function is going to be exiting first, but as we move across at a steady pace, the function is going to be, or the product of those two functions are going to be decreasing faster and faster as the slope is getting greater and greater, and that's exactly what we can see over here happening. We have an exponential decay that's getting faster and faster and faster as we move through. So if I just jump to that section over there, as we start to exit, we can see that more and more is going to be exiting at a higher rate, and that's why we have this exponential drop-off over here. And then obviously in the middle part, just over here, where there's nothing changing, it's leveling off over here. And that value, by the way, is going to be the maximum value, which we can see, over here. So when g of t takes the position when t equals 0, the product of the area under those two curves that are common are going to be something like 1.7, and that area is going to remain at about 1.7 between t and t minus 1 for all these values up until t equals 1, and then as the function starts to exit, we're going to get less and less overlap between the limits of 1 and t minus 1. So I hope that was helpful.